My dear students, I hope you are in good health at your home. Today I am going to deliver my 10th lecture on mechanics. Today I shall discuss a very important theorem called the work energy theorem. First of all, we have to know some important concepts which you already know, which you already come across. How do we go into kinetic energy? Number one, when net force acts on a body, the body accelerates, right? The body accelerates. Whenever there is force acting on a body, the body accelerates. Secondly, if we apply the force for some time, it means the body its velocity changes from initial velocity vi to vf, the final velocity. Now, a system can be analyzed using two ways. Number one, use force and displacement. Number two, use work and energy. So we have come to the point of energy. One form of energy is called kinetic energy. That is, it is energy of motion. And this kinetic energy of a body is related to the work done on the. This is the final concept we need to ponder about. Whenever work is done on a body, its kinetic energy changes. Or in other words, kinetic energy is related to the work done on the body. So now we are going to derive the work energy theorem. For this, we first consider only constant forces. Consider only constant forces. We can find the net work done in two ways. Number one, find F net equals sum over F. That means the situation is like this: you have one body. You have one body, and several forces are acting on that body. So your first job is to find the total force acting on the body. How do you find that? You do a vector sum of the individual forces and find the resultant force. That is the F net. F net is the resultant force of the forces F, and we find by doing a vector sum of the individual forces and find the F net. Number two, the second way, calculate, let me say something more about the first case. W net will be then F net dot S. S is a displacement caused by all the forces acting on that body. We have found the work done W net by first finding the net force and then making a dot product with the displacement which is caused by all the forces with the F net. The second way you can do the same calculation is calculate individual works. Say W1 is F1 dot S, W2 is F2 dot S. So W net will be W1 plus W2 plus W3 all the work done, all the individual works done. So you can find also the net work by summing the individual works. Take a single force, find the work done by this force. Take another force, find the work done by that force. In this way, you consider all the forces and individually find the work done by that force on the body. Finally, you add all the individual works, you get the W net. The first process is in two-step process. First, you find the net force. In other words, the resultant force acting on the body. Then you do not have to do any sum. Simply, you do a dot product between the F net and the displacement. In the second process, you do the calculation by individually calculating the works and then summing the individual works. That means W naught is W1 plus W2 plus W2. This way you can accomplish your work. Now, by Newton's law, F net equals m a vector. A vector is the acceleration vector. The net force produces a net acceleration. We do not give any substitute to the A or symbol A, but there will be only one acceleration. Even if separate forces work on the body, acceleration will be a single quantity. So you need not write A1, A2, A3, A4 this way. Right? F net equals Fa. Which, as the body moves, as the body moves by a displacement S, then the net force causes its velocity to change from Vi to Vm. Think deeply. By Newton's law, F net equals ma. Whenever there is acceleration, velocity changes. So since F is working, there will be acceleration. And acceleration will change the velocity. Say we take that the force begins at a particular moment I, and in that moment the velocity is Vi, and for some time the force remains to act and stops at a particular moment. The final velocity will be Vf. So whatever is conveyed, whenever one body accelerates or one force acts, the velocity of the body on which the force acts changes from an initial velocity Vi to a final velocity Vf. Now, we are considering constant forces. For constant forces, we have two simple formulas which we will apply to calculate the total work. Two simple formulas for constant forces. For constant forces, V, this is final V, is V naught plus a vector T. Also, S vector displacement is V naught T plus half A square. A is vector. Time is a scalar quantity. Time is a scalar quantity. Is a vector. So you need not put any vector sign over T. But V naught and acceleration are vector quantities. Now, what we have? We have for V naught Vi, for V Vf. Consider that in our case, V naught is the initial velocity Vi, and the V is nothing but the Vf. In this way, from this formula, we can write A equals Vf minus Vi divided by T. But we shall write it Vf minus Vi by delta T. Vf minus delta T. Because we take a small interval of time delta T to delta T. Okay? We are just changing from this formula the T is replaced by delta T. Next, we have to compute S. How do you do that? S is V naught. What is V naught in our case? Vi. What is T in our case? Delta T. Right? V naught is in our case Vi. T in our case is delta T. Plus half A. What is A? Vf minus Vi by delta T. Then what is T square? Delta T square, right? Do you agree? You agree. So the next thing will be to write this delta T and this delta T square gives you only delta T in the numerator. So I can write Vi multiplied by delta T plus half Vf minus Vi multiplied by delta T, and in the next line I can write Vi plus half Vf minus Vi. Both has common factor delta T. Both is equal to say half Vf. Here is here full, here is minus half. So I get Vf plus Vi by 2 multiplied by delta T. So this is the expression for displacement S. This is the expression for displacement S. Now we should compute the W net, the total work done. W net equals F net dot S equals M A vector dot S. M, what is A? A is Vf minus Vi by delta T. Dot. This dot is a vector dot. This is the dot. This is the dot of the dot product. This is the dot of the dot product. And S is what? You have done that. You have found that Vf plus Vi by 2 delta T. Now this delta T cancels out. These two we can take in form half M. Vf minus Vi dot Vf plus Vi. Right? are heading in the right direction. We are heading in the right direction. So far, nothing bad. Now do this dot product. VF dot product gives you VF dot VF. VI gives you VF dot VI. This and this gives you minus VI dot VI. This and this give you minus VI dot VI. Now see, VF dot VI is equals VI dot VF. This is the rule of the dot product. A dot B and vector A dot B equals B dot A. Here is what? VF dot VI, that is what? VI dot VF. So VF dot VI equals VI dot VF, and there is minus sign. So this term and this term cancels out, and you are left with half M. VF dot VF is what? VF square. The final term VI square, or equals half M V F square minus half M V I square. This is the work done by the constant force F net. This is the work done by the constant force F net on the body of mass M. The body has mass M and a constant force X upon this, and you will get the total work done by given by this formula. W that equals half M VF square minus VI square is equals half M VF square minus half M VI square. Now we define kinetic energy as K equals half M square. Here M is the mass of a body whose velocity is V. M is the mass of a body whose velocity is V. Then its kinetic energy is K equals half mv square. Okay. If this is so, I can write from India, I can write Km equals half m v square, Ki equals half m v square, and W net becomes Kf minus Ki, which is written usually delta K. So W net is equals Kf plus Ki is equals delta K, the change in kinetic energy. Whatever the kinetic energy was in the beginning, and whatever it is in the final position, you find the difference between them. What? The difference is taken from the final, you subtract the initial. From the final kinetic energy, you subtract the initial kinetic energy. This is the tricky point. Many students do the opposite thing. They find the change in something by subtracting the initial, by subtracting the final from the initial. That is wrong. Whenever you want to find the change, then subtract the initial from the final. So our journey is Kf plus Ki. This is also W net. And reminder, K is a scalar quantity because you can write K equals half and V dot V. Half and V square, half and V square is V dot V, right? V dot V is a scalar and dot product. Dot product is a scalar quantity. M is a scalar quantity. So kinetic energy is a scalar quantity. Now, from this formula, W net equals Kf minus Ki is equals delta K. We can get an important theorem which is called the work energy theorem. The work energy theory. The net work done by the forces acting on a body is equal to the change in the kinetic energy of the body. What is this? W net equals Kf minus Ki. What is this? This is the work done by the forces on the body whose kinetic energy is initially Ki, and this work changes the kinetic energy to the final kinetic energy Kf. So what happens? Whatever work is done is equal to the change in kinetic energy. Whatever work is done on the body by the forces is equal to the change in kinetic energy, Kf minus Ki. This is the work energy theorem. Next, we shall consider non-constant forces or variable forces and give a general proof of the work energy theorem. That means we should not assume that the forces are constant. We should not assume that the forces are constant. Let a force is affects F net x. F net x. No need for writing the vector sign because it acts only in the x direction. It has only one direction, x direction. So you need not write the vector sign over this because you will not encounter any other vector in this calculation. So that you have to use several vector signs. No, you do not need that. It is a one-dimensional force acting on the x direction, but there are several forces. So you add the several forces to find the F net, and then x, all of them act in the x direction, so you write F net x. So now f net x equals m x. X is the acceleration in the x direction. F was the acceleration. The acceleration will be the acceleration. This is by Newton's law. This is by Newton's law. In which direction a force x acceleration is also in that direction. So f net x equals max. Now x can be written as dvx by dt, right? Dx is the velocity in the x direction. Then you can write m dvx by dx, dx by dt. Dx cancels, you have the same thing, dx by dt. Dx, numerator, dx cancels, you have the same quantity, dvx by dt, whatever in the previous step was. Next, you can write m dvx by dx, because dx by dt equals nothing but dx, right? Next, we can write m dx dvx by dx. This is the net force. This is the net force in terms of velocity. This is the net force in terms of velocity. Now, what will the total work done? What will be the total work done? W net is integration. I have considered, I have covered this in the previous lecture. You do find the total work by integrating the f multiplied by dx, right? So W net is f net of x d. This is the formula for the work done by a variable force. This is the formula for the work done by a variable force. So what is f net x? You write m dx d dx by dx, then this dx, equals integration, m is taken out, dx cancels, dvx. The integral is over the variable dx. The integral is over the variable dx, and its result should be found between the initial velocity vi and the final velocity vf. And we should give a substring x because we want to make sure that it is a one-dimensional motion and the motion is in the x direction. So I write vix, vf. dx, dvx. Now, what is this integration? M vx square by 2 vix vfx. What will you find? Half m vfx square minus vix square. So So W net equals half M V fx square M dv square minus half M V by x square. This is again what? The work energy theorem. This is again the work energy theorem. But we have proven this for variable forces by doing an integral. The previous method was not integration, this was vectorial calculation. Now we have done an integral. By doing this integral, we have found out that W net is same as before for three-dimensional forces. For three-dimensional forces, I have put an F vector, that is a three-dimensional force, or a two-dimensional force, or a one-dimensional force. But here we have proved it for only one dimension. But rest assured that this formula is valid for 1, 2, 3 dimension. That means W equals, we will not write net anymore. We know now what is net. That means the whole one, the total one. W is Kf minus Ki. This is the work energy theorem. If some forces act on a body, then the body's velocity changes from Vi to Vf, and this quantity changes from Ki to Kf. The total work done on the body by the forces is equal to the change in kinetic energy. This is the work energy theorem. Today this much. My students, stay at home and try to maintain your health and be safe. We'll see again you in the next class. I don't know when, but I'm going to give another class in today's period. Thank you very much.